Right now, two spacecraft are sending back signals from a place no human object has ever been. They have crossed a boundary where the protective wind from our star dies, where temperatures spike to 400,000 degrees, where a wall of hydrogen is pressing in from all directions, and where radiation levels triple in an instant. This is the edge of the solar system, and the deeper we look, the stranger it gets. If you enjoy this journey, consider liking and subscribing. Now, let us begin. In 1977, two spacecraft left Earth on a mission that was only supposed to last 4 years. They were called Voyager 1 and Voyager 2. Their original job was simple: fly past Jupiter and Saturn, take photographs, collect data, and then drift into silence. Nobody expected them to survive this long. Nobody expected them to still be transmitting signals almost 50 years later. And absolutely nobody expected what they would find at the edge of our solar system. For decades, these two machines flew farther and farther from home. They passed the giant planets. They crossed the orbits of ice worlds. They entered regions of space so remote that light from our star takes hours to reach them. And then, one by one, they began to detect something strange. The environment around them started to change. This was not a dramatic explosion or a visible wall. It was subtle at first. The instruments on board began picking up shifts in particle density. The solar wind, that constant stream of charged particles flowing outward from our star, started behaving differently. It was slowing down, it was heating up, and it was colliding with something. Scientists on Earth watched the data arrive and realized the Voyagers were approaching a boundary. Not a physical barrier you could touch, but a transition zone where the influence of our star begins to fade and the influence of interstellar space begins to take over. This boundary has a name. It is called the termination shock. Think of it like the edge of a river meeting the ocean. The river does not simply stop. It collides with the larger body of water, and the collision creates turbulence, mixing, and chaos. That is what happens at the termination shock. The solar wind, which travels outward at over 1,000,000 miles per hour, slams into the pressure of interstellar space and suddenly drops to a fraction of its original speed. Voyager 1 crossed this boundary in 2004. Voyager 2 crossed it in 2007, and both spacecraft confirmed something scientists had only theorized. The edge is real, it is measurable, and it is violent. But here is where things get unsettling. When the Voyagers crossed the termination shock, they did not find what the models predicted. The temperature readings were off. The magnetic field data was confusing. The particle counts did not match expectations. Scientists had spent decades building simulations of this region, and the real thing turned out to be far more complicated. This matters to you because the termination shock is the first line of defense between our solar system and the rest of the galaxy. Everything inside this boundary is shaped by the energy of our star. Everything outside is shaped by forces we barely understand. And until the Voyagers crossed it, we had no direct evidence of what that transition actually looked like. Now we do, and it raised more questions than it answered. The data confirmed that the termination shock is not a clean, stable line. It wobbles, it shifts, it moves closer to our star and then retreats outward depending on the activity level of the solar wind. Some years it might be 8 billion miles away. Other years, it might be 10 billion miles away. The edge is not fixed. It breathes, and that breathing is influenced by something pushing back from the outside. This is the first sign that interstellar space is not passive. It is not just an empty void waiting beyond our star's reach. It is an active environment with its own pressure, its own particles, and its own magnetic fields. And it is pressing inward, constantly testing the strength of our star's protective bubble. The Voyagers taught us that we live inside a shelter, a fragile, invisible cocoon inflated by the energy of our star. And outside that cocoon, something else exists. something older, something colder, something that has been waiting for billions of years. But crossing the termination shock was only the beginning, because what the Voyagers found next made even less sense. Here is something that should not make sense. As you travel away from our star, things should get colder. That is basic physics. The farther you move from a heat source, the less energy reaches you. By the time you reach the outer solar system, temperatures plunge to hundreds of degrees below zero. Space becomes unimaginably frigid, but at the termination shock, the temperature suddenly spikes to over 400,000 degrees. This is not a mistake. This is not a sensor error. Both Voyager spacecraft recorded it, and it completely defied what scientists expected to find. To understand why this happens, you need to rethink what temperature actually means in space. When we talk about temperature on Earth, we usually mean how hot or cold something feels to the touch. That depends on how much energy is packed into the molecules around you. Air at room temperature has trillions of molecules bumping against your skin, transferring heat. But in space, there are almost no molecules. The regions near the termination shock contain roughly 1 particle per cubic inch. Compare that to the air you are breathing right now, which contains billions of trillions of particles in the same space. So even though individual particles at the termination shock are moving at extreme speeds, which is what temperature measures, there are so few of them that you would not feel any heat at all. Your skin would still freeze. You would still die from the cold. But the particles themselves are screaming with energy. This happens because of the collision. When the solar wind slams into the wall of interstellar pressure, it does not simply stop. It compresses, and compression generates heat. Think of a bicycle pump. When you push air into a tire, the pump gets warm. You are forcing particles into a smaller space, and that concentrated energy becomes heat. At the termination shock, the solar wind is being compressed by the force of interstellar space pushing back. Particles that were cruising along at 1,000,000 miles per hour are suddenly squeezed together. Their speed does not vanish. It transfers into chaotic, random motion. And that chaotic motion is what we measure as temperature. So the Voyagers flew into a region where individual atoms were vibrating with the energy of a furnace, but the space around them was still essentially empty. It is one of the strangest contradictions in our solar system, a place that is both superheated and freezing at the same time. But this discovery is not just a scientific curiosity. It matters for a very practical reason. The termination shock is where our protection starts to weaken. Inside this boundary, the solar wind dominates. It pushes outward in all directions, sweeping away dangerous particles from deep space. It creates a pressure that holds back the interstellar medium. But at the termination shock, that pressure drops, the wind slows, and the barrier becomes thinner. This means that radiation from outside our solar system has an easier time leaking through. Scientists confirmed this when they compared data from inside and outside the termination shock. Cosmic ray levels, the high-energy particles that come from exploding stars and black holes far across the galaxy, increased significantly once the Voyagers crossed into this region. The protective bubble was no longer holding them back as effectively. For humans, this is critical information. Any spacecraft traveling toward the edge of our solar system would pass through this zone. Astronauts inside would be exposed to rising radiation levels precisely in the region where temperatures appear to spike. Shielding would need to account for both the particle energy and the increasing cosmic radiation. We are only just beginning to understand what this transition zone demands, and the temperature spike is only one of the mysteries waiting there. Because just beyond the termination shock, the Voyagers found a wall. Imagine a river flowing steadily for billions of miles. It begins at the surface of our star, where temperatures reach millions of degrees and atoms are torn apart into charged particles. These particles, mostly protons and electrons, are flung outward at staggering speeds. By the time they pass Earth, they are traveling at roughly 1,000,000 miles per hour. This is the solar wind, and it never stops blowing. For decades, Scientists wondered what would happen when this wind finally met resistance. They knew it could not blow forever. At some point, the pressure of interstellar space would push back. The wind would have to slow down, but nobody knew exactly where that would happen or what it would look like. The Voyagers answered that question. When Voyager 1 crossed the termination shock in 2004, its instruments recorded a sudden and dramatic change. The solar wind speed dropped from over 1 million miles per hour to less than 250,000 miles per hour in a relatively short distance. It was like watching a supersonic jet suddenly hit a wall of thick mud. This deceleration is violent. The particles do not gently coast to a stop. They pile up, they compress, they collide with each other and with the slower moving material ahead of them. The result is a turbulent, chaotic region where energy is transferred in unpredictable ways. But here is what makes it unsettling. The slowdown is not smooth. The Voyagers recorded fluctuations. The wind speed would drop, then briefly recover, then drop again. The boundary itself seemed to ripple and shift. Scientists realized that the termination shock is not a stationary wall. It moves. It expands and contracts depending on how active our star is at any given moment. When our star is in an active phase, producing more flares and ejecting more material, the solar wind is stronger. It pushes the termination shock outward, sometimes by hundreds of millions of miles. When our star quiets down, the wind weakens, and the termination shock creeps back inward. This means the edge of our solar system literally breathes. For anyone hoping to travel to this region, this creates a problem. You cannot aim for a fixed point. The boundary you are trying to reach might move before you get there, and when you cross it, the environment changes dramatically. The slowdown of the solar wind has real consequences for spacecraft. The charged particles that make up the wind create a kind of pressure around any object moving through them. When the wind slows, that pressure changes. The forces acting on a spacecraft become less predictable. Navigation becomes more complicated. But the more troubling consequence is what happens to protection. The solar wind acts like a shield. As long as it is blowing outward at high speed, it sweeps away incoming particles from deep space. Cosmic rays, those high-energy particles from distant supernovae and black holes, have a harder time penetrating a region filled with fast-moving solar material. The wind creates drag that slows them down and deflects their paths. When the wind slows at the termination shock, that shielding weakens. The Voyagers recorded an increase in cosmic ray intensity almost immediately after crossing the boundary. The particles they detected were not coming from our star. They were coming from outside, and they were arriving in greater numbers because the wind was no longer strong enough to hold them back. For human health, cosmic rays are a serious concern. They can penetrate spacecraft hulls. They can damage DNA. They can increase cancer risk over long missions. And the data from the Voyagers confirms that radiation levels rise sharply once you leave the fast solar wind zone. This is one reason why traveling to the edge of the solar system is so difficult. You are not just dealing with distance. You are dealing with a gradual loss of protection that our star provides. The farther you go, the more exposed you become. And the termination shock is only the first boundary. Beyond it lies a region even more chaotic. There is something pressing against the edge of our solar system. It is not a spacecraft. It is not an asteroid. It is not anything solid at all. It is a wall of hydrogen atoms, and it has been building up at our doorstep for as long as our star has existed. Both Voyager spacecraft detected it. So did other instruments closer to home. And for years, scientists argued about what it actually was and where it came from. Here is what we know for certain. As our solar system moves through the galaxy, it plows through the thin gas that fills interstellar space. This gas is mostly hydrogen, the simplest and most abundant element in the universe. The atoms are spread incredibly thin, just a handful per cubic inch, but over enormous distances they add up. When these hydrogen atoms encounter the edge of our solar system, something strange happens. They slow down, they pile up, and they form a dense region that scientists call the hydrogen wall. Think of it like snow building up against a moving car. The car pushes forward, and the snow accumulates at the front. Our solar system is doing the same thing as it drifts through space at roughly 450,000 miles per hour. The hydrogen ahead of us has nowhere to go, so it compresses. This creates a region of higher density right at the boundary between our star's influence and interstellar space. The Voyagers detected this wall indirectly. Their ultraviolet instruments picked up a glow coming from the outer solar system, a faint signature that indicated extra hydrogen was present. When scientists analyzed the data, they realized the glow was too strong to come from normal interstellar gas. Something was concentrating the hydrogen. Later observations from spacecraft like New Horizons confirmed the finding. The hydrogen wall is real. It wraps around the leading edge of our solar system like a bow wave in front of a ship. But here is where it gets more interesting. Not all of the hydrogen in this wall comes from outside. Some of it comes from inside. When the solar wind reaches the outer solar system, it begins to interact with incoming interstellar material. Protons from the solar wind can steal electrons from incoming hydrogen atoms. When that happens, the protons become neutral hydrogen atoms themselves. These neutrals are no longer affected by magnetic fields, so they drift in strange directions. Some of them head back toward our star, others pile up at the boundary. The result is a mixing zone where solar material and interstellar material swap particles and create a complicated soup of atoms. This matters because the hydrogen wall affects how we see the universe. Ultraviolet light from distant stars has to pass through this wall to reach our telescopes. If the wall absorbs or scatters some of that light, it changes what we observe. Scientists had to account for this when calculating the properties of nearby interstellar gas. The wall was adding noise to their data. It also matters for any spacecraft heading outward. The hydrogen wall is not dangerous in the traditional sense. The atoms are moving too slowly to cause damage on impact, but their presence changes the environment in subtle ways. They interact with solar wind particles. They influence the shape of the heliosphere, and they mark the beginning of a transition from the familiar to the unknown. When Voyager 1 passed through this region, it was entering territory where the dominant material was no longer coming from our star. The hydrogen it encountered was ancient. Some of those atoms had been drifting through the galaxy for billions of years, produced by stars that died long before our solar system formed. You are surrounded, right now, by a bubble of material created by our star, but pressing against that bubble from all directions is older material. Material that has been waiting, and it gets even stranger, because the hydrogen wall is just the outer edge of something much larger. Between the termination shock and the true edge of our solar system lies a region of pure chaos. It is called the heliosheath, and it is nothing like scientists expected. For decades, researchers imagined this region as a smooth transition zone. They pictured the solar wind gradually fading, the interstellar medium gradually taking over, and the boundary between them as a gentle gradient. The Voyagers proved them completely wrong. When Voyager 1 entered the heliosheath in 2004, its magnetometer began recording something bizarre. The magnetic field was not smooth, it was not stable. It was broken into countless small bubbles, each one roughly 100 million miles across, tumbling and swirling in every direction. Imagine a bathtub filled with foam. Each bubble is separate, enclosed, and packed against its neighbors. Now imagine that bathtub is billions of miles wide, and the bubbles are made of magnetic force instead of soap. That is the heliosheath. This discovery shocked scientists. Their models had not predicted it. Their simulations had not shown it. The magnetic bubbles only appeared when real spacecraft flew through and sent back actual measurements. So, why do these bubbles form? It has to do with how our star rotates. Our star spins on its axis, completing one rotation roughly every 27 days. As it spins, Its magnetic field spirals outward like water from a rotating sprinkler. By the time that magnetic field reaches the outer solar system, it has become twisted and folded in complicated ways. At the heliosheath, the solar wind slows down dramatically. The magnetic field lines, which were being stretched outward by the fast wind, suddenly pile up. They fold over themselves. They reconnect in strange configurations. And the result is a frothy mess of magnetic bubbles instead of a smooth, organized field. This has real consequences for anything traveling through. Magnetic fields influence charged particles. Cosmic rays, which are mostly protons and atomic nuclei traveling at near light speed, are deflected by magnetic fields. A smooth, organized field can act like a shield, bending cosmic rays away from a spacecraft or planet. A chaotic, bubbly field does not provide the same protection. Scientists now believe that cosmic rays can actually hop from bubble to bubble, finding pathways through the heliosheath more easily than they would through a smooth barrier. This means the protective effect of this region is weaker than we hoped. For astronauts on a deep space mission, this is bad news. The heliosheath was supposed to offer some shielding. Instead, it might be more like a sieve, letting dangerous radiation leak through the gaps between bubbles. But the bubbles are not the only surprise. The heliosheath is also home to massive pressure waves. When our star releases a coronal mass ejection, a giant burst of plasma and magnetic field, that wave travels outward through the solar system. Eventually, it reaches the heliosheath and slams into the slower-moving material there. Voyager 1 detected several of these pressure waves. Each one caused the magnetic field around the spacecraft to spike and fluctuate. Each one took months or even years to pass. And each one revealed just how dynamic this region really is. The heliosheath is not a quiet waiting room before interstellar space. It is an active, violent environment where energy from our star collides with energy from the galaxy. The bubbles churn, the pressure waves ripple, and caught in the middle of it all, two tiny spacecraft continue to send back data. They have been traveling through the heliosheath for years, and what they found at the far edge is even harder to explain. Something invisible is trying to kill you. Right now, as you listen to this, high-energy particles are streaming through space at nearly the speed of light. They are protons stripped from atoms by supernova explosions. They are nuclei forged in the cores of dying stars. They are cosmic rays, and they are everywhere. On Earth, you are protected. The planet's magnetic field deflects most of them. The atmosphere absorbs the rest. But in space, outside the shelter of our planet, cosmic rays become one of the deadliest threats a human could face. And at the edge of the solar system, their intensity triples. The Voyagers confirmed this as they crossed into new territory. Their cosmic ray detectors tracked the incoming particles at every stage of the journey. Inside the termination shock, levels were manageable. Inside the heliosheath, they began to rise. But once the spacecraft crossed the heliopause and entered true interstellar space, the numbers jumped dramatically. Voyager 1 saw cosmic ray intensity increase by roughly 300% compared to what it measured in the inner solar system. The protective bubble generated by our star was no longer filtering them out. This is not a minor detail. This is a fundamental barrier to human exploration. Cosmic rays are not like ordinary radiation. They carry enormous energy. A single cosmic ray particle can have more energy than a baseball thrown by a professional pitcher, all concentrated in something smaller than an atom. When these particles hit a spacecraft hull, they do not simply bounce off. They blast through, shattering atoms in their path and creating showers of secondary particles. When they hit living tissue, they damage cells, they break DNA strands, they increase the risk of cancer, neurological damage, and other health problems. Short exposure might be survivable. Long exposure, like a multi-year mission to the outer solar system, could be fatal. The heliosphere, that bubble of solar wind and magnetic field surrounding our star, acts as a partial shield. It does not stop all cosmic rays, but it slows them down and deflects many of them away. Once you leave the heliosphere, that shield disappears. This is why the Voyager measurements matter so much. Before we had real data, scientists could only estimate how bad the radiation environment would be at the edge. Now we know, and it is worse than some of the optimistic predictions suggested. Any crewed mission to the outer solar system would need unprecedented radiation shielding. Current spacecraft are not built to handle this level of exposure for extended periods. The materials required to block cosmic rays are heavy and expensive. Water, polyethylene, and certain metals can help, but you would need thick layers of them surrounding the entire crew compartment. This adds mass. Mass requires more fuel. More fuel requires larger rockets. The engineering challenges compound quickly. And shielding is not even a perfect solution. Some cosmic rays are so energetic that nothing realistic can stop them. They will punch through meters of material and still reach the crew inside. The only defense against those is limiting exposure time. This creates a terrible equation. The farther you travel from our star, the weaker the natural shielding becomes and the longer the mission takes. You cannot escape by going faster because we do not have engines capable of the speeds required. You are stuck in a slow crawl through an increasingly hostile environment. The Voyagers do not have this problem. They are machines. Radiation damages their instruments over time, but they have no cells to mutate, no organs to fail. They can drift through interstellar space for thousands of years without caring about cosmic rays. Humans are not so fortunate, and the radiation is only one of the dangers waiting beyond the heliosphere. Voyager 1 did not cross the edge of the solar system once. It crossed it multiple times. This is one of the strangest discoveries from the entire mission. Scientists expected the heliopause, the boundary where the solar wind stops and interstellar space begins, to be a clear transition. You would be inside the heliosphere, and then you would be outside. The change would happen once and be permanent. That is not what happened. In the months leading up to the official crossing in 2012, Voyager 1's instruments recorded a series of bizarre fluctuations. The spacecraft would detect a sudden drop in solar particles and a spike in cosmic rays, suggesting it had entered interstellar space. Then, hours or days later, the readings would reverse. Solar particles would return. Cosmic rays would drop. It was as if the spacecraft had slipped back inside the bubble. This happened several times before the final crossing. Scientists realized that the heliopause is not a rigid wall. It is more like a membrane, flexible and reactive, constantly shifting in response to pressure from both sides. When the solar wind strengthens, the membrane pushes outward. When interstellar pressure increases, the membrane compresses inward. Voyager 1 happened to arrive during a period of instability, and it experienced the boundary moving back and forth across its position. Think of it like standing in the ocean at the edge of the surf zone. Sometimes a wave washes over your feet, sometimes the water retreats. You are not moving, but the boundary between wet and dry keeps shifting around you. For the scientists tracking Voyager 1, this was both exciting and frustrating. They wanted a clean moment to announce. They wanted to say the spacecraft had officially left the solar system on a specific date, but the data kept contradicting itself. Eventually, they settled on August 25, 2012, as the official crossing date. That was when the solar particle count dropped permanently and the cosmic ray count stayed elevated. The spacecraft had finally pushed through the last flicker of the membrane and entered true interstellar space. But the flickering raised important questions. If the heliopause is unstable, what does that mean for long-term protection? Could there be moments when the bubble contracts dramatically, exposing the outer planets to higher radiation? Could a strong enough interstellar pressure wave push the boundary inward by a significant amount? Scientists believe the answer to both questions is yes. Over geological timescales, the heliosphere has almost certainly changed size. When our star was younger and more active, the bubble was probably larger. When it passes through denser regions of interstellar gas, the bubble compresses. There may have been periods in Earth's history when the outer edge of the solar system was much closer than it is today. This could have affected life on our planet. Higher cosmic ray levels are linked to increased cloud formation, which can change climate. Some researchers have speculated that passages through dense interstellar clouds could have triggered ice ages or extinction events. The evidence is not conclusive, but the possibility is disturbing. Right now, we are protected. The heliosphere extends billions of miles in every direction, but that protection is not permanent. It depends on the strength of our star, the pressure of the surrounding medium, and factors we do not fully control. The voyagers showed us that the edge is not fixed, and beyond that flickering boundary, something even stranger was waiting. In 2009, NASA launched a small spacecraft called IBEX. Its mission was simple: point instruments at the edge of the solar system and map what was out there. No one expected it to find something impossible to explain, but that is exactly what happened. IBEX detected a giant ribbon of energy stretched across the sky. It was not predicted by any model. It did not match any existing theory. And after more than a decade of study, scientists still do not fully understand what it is. Here is what we know. The ribbon appears in data collected by instruments that detect energetic neutral atoms. These are particles created when fast-moving ions from the solar wind collide with slower hydrogen atoms in interstellar space. The collision strips the ion's charge, turning it into a neutral atom that can travel in a straight line without being bent by magnetic fields. IBEX catches these atoms and traces them back to their origin. When scientists assembled the data into a map, they expected to see a relatively uniform glow from all directions. Instead, they found a bright band cutting across the sky, roughly circular, spanning about 300 degrees of arc. It was 2 to 3 times brighter than the surrounding regions. Nothing in the models had predicted this. The ribbon appears to be aligned with the direction of the local interstellar magnetic field. This suggests the field is somehow focusing or enhancing the emission in that particular region, but the exact mechanism remains unknown. One leading theory suggests that solar wind particles are getting trapped in the interstellar magnetic field. Instead of scattering randomly, they bounce back and forth along field lines, accumulating in a specific zone. When they eventually neutralize and fly back toward the inner solar system, they create the bright ribbon IBEX detected. But this explanation has problems. The brightness is higher than predicted, the shape is more distinct than expected, and some features of the ribbon change over time in ways the theory does not fully explain. Other theories propose different mechanisms. Some suggest the ribbon marks a boundary where two different magnetic field regions meet. Others propose it involves interactions between the heliosphere and a nearby interstellar cloud. None of these ideas have been confirmed. What makes this discovery so unsettling is what it implies about our understanding of the local environment. We thought we knew the general structure of the space around us. We had decades of data from various spacecraft. We had sophisticated computer models. And then IBEX looked at the edge of the solar system and found something completely unexpected. This means our models are incomplete. The ribbon is not just a curiosity. It is evidence that something is happening at the boundary of our solar system that we did not anticipate. Some force, some structure, some interaction is creating a pattern that defies our current understanding. And this has practical implications. If we do not understand the local interstellar environment, we cannot accurately predict what spacecraft will encounter as they travel outward. We cannot model radiation exposure correctly. We cannot plan missions with confidence. The ribbon is a reminder that the universe does not care about our expectations. IBEX is still operating, still collecting data, still refining our maps of the edge. Future missions may help solve the mystery, but for now, the ribbon remains one of the most puzzling discoveries in solar system science, and it is only one piece of a much larger puzzle. We are not sitting still. This is easy to forget. When you look at the night sky, the stars seem fixed, the darkness seems permanent, but everything is moving. Our planet orbits our star. Our star orbits the center of the galaxy, and the entire solar system is drifting through a vast, invisible cloud of gas and dust. It is called the local interstellar cloud, and it is mildly radioactive. This cloud is roughly 30 light-years across. It contains thin wisps of hydrogen, helium, and trace amounts of heavier elements. The density is incredibly low, only about 1 atom per 5 cubic inches. But over the enormous distances of space, that adds up to a significant amount of material, and our solar system is plowing through it at roughly 50,000 miles per hour. Scientists estimate we entered this cloud sometime within the last few thousand years. Before that, we were traveling through an even emptier region of space called the local bubble, a vast cavity blown out by ancient supernova explosions. The transition from the empty bubble to the denser cloud has subtle effects on the heliosphere. The cloud's material presses against the edge of our solar system. It provides the resistance that shapes the termination shock and the heliopause. It contributes to the hydrogen wall building up at our bow. In a very real sense, the local interstellar cloud is constantly interacting with the protective bubble around our star. But here is the unsettling part. The cloud contains trace amounts of radioactive isotopes. These are atoms with unstable nuclei that decay over time, releasing radiation. The quantities are small, and the danger to life on Earth is negligible because we are protected by the heliosphere, our planet's magnetic field, and our atmosphere. But the presence of these isotopes tells us something about the cloud's history. Radioactive elements in interstellar space typically come from supernova explosions. When a massive star dies and blows itself apart, it creates heavy elements through nuclear fusion and scatters them across space. Some of those elements are radioactive. Finding them in the local interstellar cloud means this material was enriched by stellar explosions in the relatively recent past. Scientists have detected some of these isotopes in deep ocean sediments on Earth. Iron-60, for example, is a radioactive form of iron that does not occur naturally on our planet. Finding it in the geological record suggests that particles from the local interstellar cloud have occasionally made it through all our protective layers and reached the surface. This is not an immediate threat. The quantities are tiny, but it is a reminder that we are connected to the larger galactic environment in ways we often forget. The local interstellar cloud will not last forever. At our current speed, we will exit it within the next 10 to 20,000 years. Then we will enter whatever lies on the other side. It might be another cloud. It might be empty space. We do not know yet. What we do know is that our passage through different interstellar environments can affect the heliosphere. Denser regions compress the bubble. Emptier regions let it expand. Over millions of years, these changes could influence conditions in the outer solar system and potentially even the inner planets. We are travelers, whether we realize it or not. And the road ahead holds more surprises. When Voyager 1 finally crossed into interstellar space, it entered a region that had been waiting for billions of years. The particles surrounding it were not created by our star. They were not born in our solar system. They came from somewhere else entirely, and some of them are older than our planet. This is one of the most profound realizations from the Voyager mission. The moment the spacecraft crossed the heliopause, it began sampling material from the wider galaxy. And that material tells a story stretching back to the deaths of ancient stars. Interstellar space is not empty. This is a common misconception. When people imagine the void between stars, they picture absolute nothingness, perfect vacuum, pure darkness. But the reality is more complex. There is matter out there, not much of it, just a few atoms per cubic inch, but over the vast distances between stars, those atoms add up. Most of this matter is hydrogen. About 90% of interstellar gas consists of the simplest element in existence, the building block from which everything else is made. Another 9% is helium, the second simplest element, and the remaining 1% contains traces of heavier things: carbon, oxygen, iron, silicon. Where did these heavier elements come from? They were forged inside stars. Billions of years ago, massive stars burned through their nuclear fuel and collapsed. Some of them exploded as supernovae, scattering their guts across space. Others shed their outer layers more gently, puffing out shells of enriched gas. Over time, this processed material mixed with the primordial hydrogen left over from the Big Bang, and today, that mixture fills interstellar space. When Voyager 1 samples the particles around it, it is touching material that cycled through stellar furnaces before our solar system even formed. Some of those atoms might have been inside a star that exploded when the dinosaurs were alive. Others might date back to the earliest generations of stars in the galaxy. This is not poetry. This is measurable science. Voyager 1 carries instruments that can identify the composition of incoming particles. The data confirms that the interstellar medium contains exactly what theory predicted: hydrogen, helium, and small amounts of heavier elements. The ratios match what we would expect from billions of years of stellar processing. But there are also anomalies. Some of the cosmic rays Voyager detects have energies that suggest they originated from extremely violent events, possibly the jets of distant black holes or the shock waves of supernovae in other parts of the galaxy. These particles have been traveling for millions of years, bouncing off magnetic fields, gradually making their way to our corner of space. When they finally arrive, they carry information about events we will never witness directly. In a sense, interstellar space is a library. The particles filling it are records of everything that has happened in the galaxy: stellar explosions, black hole mergers, the slow deaths of red giants, the violent births of neutron stars. All of these events leave signatures in the cosmic ray population and the interstellar gas. Voyager 1 is reading that library. One particle at a time, it is decoding the history of our galaxy, and it is doing so completely alone, farther from home than any human-made object has ever been. But distance is relative. Compared to what lies beyond, Voyager has barely left the porch. When Voyager 1 crossed into interstellar space, scientists expected the magnetic field to change. They were right. It did change, but not in the way they predicted. Inside the heliosphere, the magnetic field is dominated by our star. The field lines spiral outward, twisted by the star's rotation, and they point in a consistent general direction. Scientists knew that once Voyager crossed the heliopause, it would encounter the interstellar magnetic field, which should point in a different direction. The problem is that the direction Voyager measured does not match what models predicted. According to observations of distant pulsars and other astronomical sources, the local interstellar magnetic field should be tilted at a certain angle relative to the plane of the galaxy. When Voyager 1's magnetometer began reporting data from interstellar space, the field direction was off. It was rotated compared to expectations. This discrepancy has sparked years of debate. One possibility is that our models of the local interstellar field were simply wrong. We inferred the field direction from indirect measurements, and those measurements might have errors. Voyager is providing the first direct sampling, and direct data trumps indirect estimates. Another possibility is that the heliosphere itself distorts the interstellar field. As our star plows through the surrounding medium, its magnetic bubble might bend the field lines, creating a transition zone where directions gradually shift. Voyager could be measuring this distorted region rather than the true undisturbed interstellar field. A third possibility is that something more complex is happening. The interstellar medium is not uniform. It contains pockets of different density, temperature, and magnetic properties. Voyager might be passing through a local anomaly that does not represent the broader interstellar field. Scientists are still analyzing the data. What makes this mystery significant is what it reveals about our knowledge gaps. We have studied the galaxy for centuries. We have mapped magnetic fields across vast distances. We thought we understood the local environment reasonably well. Then a single spacecraft took direct measurements and found something unexpected. The magnetic field is not just a scientific curiosity. It shapes how particles move through space. It influences cosmic ray propagation. It affects the structure of the heliosphere. If our understanding of the interstellar field is wrong, then our models of all these phenomena need revision. This is humbling. We sent Voyager to explore the edge of the solar system, and one of its most important discoveries is that we were wrong about basic properties of the space around us. Not dramatically wrong, but wrong enough to matter. Wrong enough that scientists had to revise their assumptions. The magnetic field data continues to stream back from both Voyagers. Each new measurement adds to the puzzle. Eventually, patterns may emerge that explain the discrepancies, or new mysteries may appear that make the situation even more confusing. For now, we know that interstellar space has a magnetic personality we did not fully anticipate, and that personality shapes everything that happens at the edge. In 2003, astronomers discovered an object that should not exist where they found it. Its name is Sedna, and its orbit makes no sense. Sedna is a chunk of rock and ice roughly 600 miles across. It orbits our star on an incredibly elongated path, swinging from about 76 times the distance between Earth and our star at its closest approach to over 900 times that distance at its farthest point. One complete orbit takes approximately 11,000 years. The problem is that Sedna never gets close enough to any known planet to have been pushed into this orbit. When scientists discover an object with a strange orbit, they usually look for gravitational interactions that could explain it. Jupiter regularly flings comets and asteroids onto unusual paths. Neptune has pushed many icy bodies into the Kuiper belt. Close encounters with planets can reshape orbits dramatically. But Sedna's closest approach to our star is still far beyond Neptune's orbit. It never comes close enough for any planet to significantly affect it. So how did it get there? Several theories have been proposed. One possibility is that Sedna was captured from another star. Early in the solar system's history, our star likely formed in a cluster with other young stars. Those stars were much closer together than stars are today. A passing star could have brought Sedna with it, and our star's gravity could have captured the object as the other star moved away. Another possibility is that a large, undiscovered planet exists in the outer solar system. This hypothetical world, sometimes called Planet 9, could have gravitationally shepherded Sedna and similar objects into their current orbits. If Planet 9 exists, its gravity would explain several puzzling features of the outer solar system. A third possibility involves the gravitational influence of the galaxy itself. Over billions of years, the tidal forces from the Milky Way can gradually alter orbits in the outer solar system. Sedna might have been nudged into its current path by these slow, cumulative effects. None of these theories have been confirmed. What we know for certain is that Sedna exists, and its orbit points to something we have not yet found. Either a planet is hiding in the darkness, or our star had a more interesting history than we realized, or the galaxy itself is sculpting the outer solar system in ways we are only beginning to understand. Sedna is not alone. Astronomers have found other objects with similarly extreme orbits. Each one adds to the mystery. Each one suggests that the outer solar system contains secrets we have not uncovered. Finding those secrets is difficult. Objects like Sedna are incredibly faint. They reflect almost no light because they are so far from our star. Detecting them requires powerful telescopes, patience, and luck, but every discovery pushes our understanding further, and one possibility looms larger than the rest. There might be another planet in our solar system, not a small one, a world 5 to 10 times the mass of Earth, orbiting so far from our star that it has never been seen. It is called Planet 9, and the evidence for its existence is growing. Here is why scientists think it might be real. In the outer solar system, beyond Neptune, there is a population of icy objects with extremely elongated orbits. These are called extreme trans-Neptunian objects. When astronomers plotted their paths, they noticed something strange. The orbits were not randomly distributed. They were clustered together, aligned in a way that suggested something was organizing them. Random chance could not explain the clustering. The odds were less than 1 in 10,000. Something had to be responsible. Computer simulations showed that a massive planet on a distant, elliptical orbit could produce exactly this pattern. Its gravity would shepherd the smaller objects, gradually pulling their orbits into alignment over millions of years. The simulations predicted the approximate mass, distance, and orbital parameters this planet would need. The numbers are staggering. Planet 9, if it exists, likely orbits between 200 and 800 times the distance from Earth to our star. One complete orbit would take 10,000 to 20,000 years. At that distance, it reflects almost no light. It is essentially invisible to current telescopes unless we know exactly where to look. This is why it has not been found yet. Searching for Planet 9 is like looking for a single dark grain of sand on a vast beach at night. The object would be faint, slow-moving, and lost among millions of background stars and galaxies. Astronomers have dedicated significant telescope time to the search, but so far, no confirmed detection has been made. Some scientists remain skeptical. They argue that the orbital clustering might be an observational bias, caused by the way we search for distant objects rather than a real physical effect. Others propose alternative explanations that do not require an unseen planet. But the circumstantial evidence keeps accumulating. Beyond the orbital clustering, Planet 9 could explain other mysteries. The unusual tilt of our star's rotation axis, the existence of objects like Sedna, and certain features of the Kuiper belt all fit better if a massive outer planet is included in the models. If Planet 9 is real, it would change our understanding of the solar system's history. Current theories suggest the solar system formed with 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. A 5th giant would require revising those theories. Perhaps Planet 9 formed closer in and was ejected outward. Perhaps it was captured from another star. Perhaps it formed in place, and we simply never knew it existed. The search continues. New telescopes are coming online that might have the sensitivity to detect Planet 9 if it exists. Survey projects are systematically scanning the sky. Machine learning algorithms are helping astronomers sift through massive datasets. Somewhere in the darkness, billions of miles from our star, a world might be waiting to be found, and if it is there, it is not alone. The true edge of the solar system is not where most people think. It is not at Pluto. It is not at the heliopause. It is not even at the orbit of Sedna. The true edge lies almost 100 times farther, in a region so distant that objects there take millions of years to complete a single orbit. This region is called the Oort cloud, and it is one of the most mysterious places in the solar system. We have never directly observed the Oort cloud. No spacecraft has visited it. No telescope has imaged its contents. Everything we know comes from inference, from studying the comets that occasionally fall inward and tracing their paths back to their origin. Here is what the evidence suggests. The Oort cloud is a vast, spherical shell of icy objects surrounding our star. It begins roughly 2,000 times the distance from Earth to our star and extends outward to perhaps 100,000 times that distance. At its outer edge, the gravitational influence of our star becomes comparable to the gravitational pull of passing stars and the galaxy itself. Scientists estimate the Oort cloud contains trillions of objects. Most are small, a few miles across at most. They are composed of ice and rock, frozen remnants from the formation of the solar system that were flung outward by the gravity of the giant planets. These objects orbit our star, but barely. Their paths are so elongated and their motion so slow that they are essentially drifting in the gravitational no man's land between our star and the rest of the galaxy. The outer edge of the Oort cloud reaches roughly 1 light-year from our star. The nearest star, Proxima Centauri, is about 4 light-years away. This means the Oort cloud extends almost a quarter of the way to the nearest stellar neighbor. For perspective, light takes about 8 minutes to travel from our star to Earth. It takes over a year to reach the outer Oort cloud. Voyager 1, traveling at roughly 38,000 miles per hour, will not reach the inner edge of the Oort cloud for another 300 years. It will take another 30,000 years to pass through it completely. The Oort cloud is not just distant, it is incomprehensibly vast, and it is the source of the most dangerous visitors to the inner solar system. Long-period comets, the ones that appear unexpectedly with orbital periods of thousands or millions of years, originate in the Oort cloud. Something nudges them from their stable paths, either the gravitational pull of a passing star, the tidal forces of the galaxy, or random perturbations from neighboring objects. Once nudged, they begin falling inward, picking up speed as they approach our star. Some of these comets pass harmlessly through the solar system and return to the outer darkness. Others strike planets. Over billions of years, Oort cloud comets have delivered water and organic molecules to the inner solar system. They have also caused extinction events. The Oort cloud is both a reservoir and a threat, and it connects us to forces far beyond our star's control. There is a slow-motion danger approaching from the darkness. Every few 100,000 years, a star passes close enough to our solar system to disturb the Oort cloud. When that happens, billions of icy objects that have drifted peacefully for millions of years can be knocked onto new trajectories. Some of those trajectories lead directly toward the inner solar system. This is not speculation. This is measured science. Astronomers have used data from the Gaia spacecraft, which precisely maps the positions and motions of over 1 billion stars in our galaxy, to identify which stars have passed near our solar system in the past and which will approach in the future. The results are sobering. On average, a star passes within 1 light-year of our star roughly every 100,000 years. At that distance, its gravity is strong enough to perturb the outer Oort cloud. Closer passages are rarer but more dangerous. A star passing within half a light-year could send significant numbers of comets cascading inward. The effects are not immediate. Oort cloud objects move slowly. A comet nudged today might take 1 million years to reach the inner solar system. But over geological timescales, these perturbations add up. The rate of comet impacts on Earth fluctuates over millions of years, and some researchers believe these fluctuations correlate with stellar passages. This could have profound implications for life on our planet. Mass extinctions in Earth's history show a rough periodicity of about 26 to 30 million years. Some scientists have proposed that this periodicity might be linked to our solar system's motion through the galaxy, which causes periodic increases in stellar encounters and Oort cloud disturbances. The theory is controversial, the evidence is incomplete, but the underlying physics is sound. Passing stars do affect the Oort cloud, disturbed comets do fall inward, and some of those comets do hit planets. The dinosaurs were wiped out by an asteroid or comet impact 66 million years ago. That object came from somewhere. It might have been nudged toward Earth by a stellar encounter millions of years before impact. We cannot stop this process. Stars move on their own trajectories. The galaxy does not care about our survival. But we can monitor the situation. We can track nearby stars. We can identify objects heading inward with enough warning to potentially deflect them. This is one reason why mapping the outer solar system matters. The more we understand about the Oort cloud and its dynamics, the better we can predict and prepare for future threats. The danger is real but slow. Any given generation has a minuscule chance of experiencing a major impact from an Oort cloud comet, but over millions of years, the odds become certainty. Something will come. The only question is when. Not all planets orbit stars. Some drift alone through the galaxy, unbound to any system, wandering the darkness between stellar neighborhoods. They are called rogue planets, and astronomers believe they outnumber stars in the Milky Way. This is a relatively recent discovery. For most of history, scientists assumed planets could only form in orbit around stars. The standard model involved gas and dust collapsing into a rotating disk, with planets gradually assembling from the material. A planet needed a star to exist. Then observations started challenging that assumption. Astronomers began detecting massive objects drifting through space with no parent star. At first, these were classified as brown dwarfs, failed stars that never ignited nuclear fusion. But as detection techniques improved, smaller and smaller objects were found. Some were clearly planet mass, too small to ever have been stars. The current estimate is startling. There may be billions or even trillions of rogue planets in our galaxy alone. Many of them likely formed normally around stars and were then ejected by gravitational interactions. Others may have formed independently, collapsing directly from clouds of gas without ever belonging to a stellar system. Here is why this matters. For the outer solar system, if rogue planets are common, then the odds of one passing through or near our solar system over billions of years are not negligible. Such an encounter could be catastrophic. A planet mass object passing through the Kuiper belt or Oort cloud would scatter objects everywhere, potentially sending a wave of debris toward the inner solar system. Even a distant passage could cause problems. Gravitational perturbations from a rogue planet could destabilize orbits, shift the positions of outer solar system objects, and alter the dynamics of the entire region. Could a rogue planet be out there right now, drifting through the outer solar system without our knowledge? It is possible. Detecting rogue planets is extremely difficult. They emit almost no light. They cannot be seen in reflected starlight because they have no star to reflect. The only way to find them is through their gravitational effects, or, rarely, through the faint infrared glow of their residual heat. Current surveys are not sensitive enough to detect most rogue planets. One could be passing through the outer Oort cloud right now, and we would have no idea unless it happened to occlude a distant star or disturb the orbit of an object we are tracking. This is an unsettling blind spot. We have mapped the inner solar system in extraordinary detail. We can track asteroids a few feet across, but in the outer regions, beyond Neptune, our vision fails. The darkness hides objects we cannot see with current technology. Future telescopes may change this. Infrared surveys could detect the faint heat signatures of nearby rogue planets. Gravitational surveys could identify their effects on known objects. But for now, we are largely blind to what might be drifting through the outer darkness. The solar system is not as isolated as it seems, and the neighborhood is more crowded than we thought. A star is coming. Its name is Gliese 710, and it is currently about 64 light-years away. That sounds like a safe distance. It is not heading directly at us. It will not collide with our star. But it is on a trajectory that will bring it closer to our solar system than almost any star has been in millions of years. In approximately 1.3 million years, Gliese 710 will pass within 10,000 astronomical units of our star. An astronomical unit is the distance from Earth to our star, about 93 million miles. 10,000 astronomical units puts Gliese 710 well inside the outer Oort cloud. This is close enough to cause serious disruption. Gliese 710 is not a small star. It is a red dwarf with roughly 60% the mass of our star. When it passes through the Oort cloud, its gravity will sweep through trillions of icy objects like a hand through a pile of sand. Some will be flung outward, ejected from the solar system entirely. Others will be nudged inward, their orbits altered just enough to send them falling toward the inner planets. Computer simulations suggest the encounter could increase the number of comets entering the inner solar system by a factor of several times. The elevated comet flux would persist for millions of years as the disturbed objects slowly make their way sunward. For any life on Earth at that time, this could be dangerous. More comets mean more chances of impact. More impacts mean more extinction-level events. The geological record shows that life on Earth is resilient but not invulnerable. A sustained increase in comet bombardment could stress ecosystems beyond their breaking point. But there is good news. 1 million years is a long time. Human civilization is only a few thousand years old. The technology we have developed in the last century would have seemed like magic to people 100 years ago. What we will be capable of in 1 million years is completely beyond imagination. If humanity survives that long, and if we maintain technological progress, we will almost certainly have the ability to detect and deflect incoming objects. The threat from Gliese 710 is real but manageable. It is a problem for our distant descendants, not for us. Still, the encounter is a reminder that the solar system is not a closed environment. We share the galaxy with hundreds of billions of other stars, all of them moving on their own trajectories, all of them capable of affecting us if they pass close enough. Gliese 710 is the nearest future approach we know about, but it is almost certainly not the only star that will ever threaten the Oort cloud. Over billions of years, there will be others. Some may pass even closer. Some may arrive sooner. The galaxy is dynamic. The darkness between stars is not a barrier. It is a highway, and traffic never stops. For decades, something was pulling our spacecraft backward. It was subtle. It was tiny. But it was real. And for years, nobody could explain it. The mystery began with Pioneer 10 and Pioneer 11, two spacecraft launched in the early 1970s to explore Jupiter and Saturn. After completing their primary missions, they continued outward, becoming the first human-made objects to travel toward the edge of the solar system. As they flew farther from our star, engineers on Earth tracked their positions with extraordinary precision. Radio signals bounced back and forth, and the Doppler shift of those signals revealed exactly how fast the spacecraft were moving and in what direction. That is when the anomaly appeared. Both Pioneer spacecraft were slowing down slightly faster than they should have been. The deceleration was tiny, roughly 10 billionths of a meter per second squared. That is an almost unimaginably small force. But over years and billions of miles, it added up. By the time Pioneer 10 was deep in the outer solar system, it was roughly 250,000 miles behind where gravitational calculations said it should be. Something was wrong. Scientists checked and rechecked the math. They accounted for every known force: the gravity of planets, the pressure of sunlight, the drag of interplanetary dust. Nothing explained the discrepancy. The spacecraft were being slowed by something invisible. For over 30 years, the Pioneer anomaly was one of the great mysteries of space science. Some researchers proposed exotic explanations. Perhaps gravity worked differently at large distances. Perhaps new physics was needed to explain the deceleration. Perhaps dark matter was somehow involved. Papers were written, theories were proposed, debates raged at scientific conferences. The stakes were high because the anomaly, if real, suggested our understanding of gravity might be incomplete. Einstein's theory of general relativity is one of the most tested theories in all of science. If Pioneer was revealing a flaw, the implications would be enormous. But extraordinary claims require extraordinary evidence. In 2012, a team of scientists finally solved the mystery. The answer was not exotic, it was thermal. The Pioneer spacecraft were powered by plutonium. The radioactive decay generated heat as a byproduct. That heat radiated away from the spacecraft in all directions. But the design of the spacecraft meant slightly more heat radiated from the front than from the back. Heat is energy. Energy carries momentum. When more photons radiated forward than backward, they created a tiny push in the opposite direction, slowing the spacecraft down. The effect was minuscule, but it matched the observed anomaly almost exactly. The mystery was solved. This might seem like an anticlimactic ending, but the Pioneer anomaly taught us something important. At the edge of the solar system, even the tiniest forces matter. Effects that would be completely insignificant near Earth become detectable over billions of miles and decades of flight time. Any future mission to the outer solar system will need to account for these forces. Thermal radiation, outgassing, even the momentum of radio signals can affect trajectory. Precision navigation becomes extraordinarily difficult when you are so far from home. The Voyager spacecraft have their own tracking challenges. Their plutonium power sources are decaying, their signal strength is fading. Engineers have to extract meaningful data from whispers across billions of miles of space. Every measurement is a triumph, and every anomaly, even one that turns out to have a mundane explanation, reminds us how much we still have to learn. Because out at the edge, the rules are different. When Voyager 1 sends a signal home, nobody hears it for almost a full day. That is how far away it is. Light itself, the fastest thing in the universe, takes over 22 hours to travel from the spacecraft to Earth. A round-trip communication, sending a command and receiving a response, takes nearly 2 days. This is the reality of deep space communication. Voyager 1 is currently more than 15 billion miles from Earth. To put that in perspective, if you could drive a car at highway speed without stopping, it would take over 25 million years to reach the spacecraft. Even at the speed of a commercial jet, the journey would take 2 million years. Nothing built by humans has ever been so far away. The signals Voyager sends are faint beyond imagination. The spacecraft transmits with roughly 23 watts of power, about the same as a refrigerator light bulb. By the time that signal crosses 15 billion miles, it has spread out so much that the energy reaching Earth is measured in fractions of a billionth of a watt. Detecting it requires the largest radio dishes on the planet. NASA uses the Deep Space Network, a collection of massive antennas in California, Spain, and Australia. These dishes are designed specifically to pick up whispers from the outer solar system. They can detect signals so weak that the natural noise of their own electronics is billions of times stronger. Even with these antennas, communication with Voyager is becoming increasingly difficult. The spacecraft's power supply is dying. Both Voyagers are powered by radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. When the spacecraft launched in 1977, these generators produced about 470 watts of power. Today, they produce less than half that. Every year, the output drops by roughly 4 watts as the plutonium decays. NASA engineers have had to shut down non-essential instruments to conserve power for the most important systems. Heaters have been turned off. Backup systems have been deactivated. The spacecraft are slowly going cold. By the early 2030s, there may not be enough power to operate any instruments at all. The Voyagers will fall silent. Until then, every bit of data they send is precious. Each signal carries information about a region of space no human will visit for centuries, perhaps millennia. Each measurement helps scientists understand the environment at the edge of the solar system and beyond. Each transmission is a gift from machines that have far outlived their expected lifespan. The time delay creates a strange relationship. When engineers send a command to Voyager, they have to wait 2 days to see if it worked. If something goes wrong, by the time they learn about it, the problem is already 2 days old. Troubleshooting is slow, methodical, and nerve-wracking, and yet the spacecraft keep working. Voyager 1 and Voyager 2 are technological marvels. Built with 1970s technology, they have survived radiation, temperature extremes, and nearly 50 years of continuous operation. Their systems are more primitive than a modern smartphone, but they are still functioning. They will not last forever. Nothing does. But while they still speak, we listen. From where Voyager 1 floats right now, our star is just a bright point of light. It is not a disk. It is not a blazing furnace dominating the sky. It is a dot, brilliant compared to other stars, yes, but still just a dot, small enough that you could block it out with your thumbnail held at arm's length. This is what isolation looks like. On Earth, we are bathed in light and warmth from our star. It fills the sky. It drives our weather, powers our ecosystems, and makes life possible. We cannot look directly at it without damaging our eyes. It is overwhelming, At Voyager's distance, it is almost humble. The spacecraft receives about 1/6000th the light that reaches Earth. That is still enough to create faint shadows, still enough to distinguish from the background stars, but barely. In a few hundred years, as Voyager drifts farther, our star will fade to the point where it is just one among many, a moderately bright star in an unremarkable constellation. From the Oort cloud, our star would be a faint speck, its warmth imperceptible, its gravity a gentle suggestion rather than a commanding force. From the nearest neighboring star, it would be invisible to the naked eye without careful searching. This is the true scale of cosmic distance. We think of our star as the center of everything. It is the anchor of our solar system, the source of all our energy, the thing around which our entire world revolves. And it is here. But out there, in the vast spaces between stars, it is nothing special. One yellow dwarf among billions. When Voyager took its famous pale blue dot photograph in 1990, it captured Earth from about 4 billion miles away. Our planet appeared as a tiny speck, less than a single pixel, suspended in a beam of light. Carl Sagan wrote movingly about what that image meant for human perspective. But Voyager is now almost 4 times farther than it was when that photo was taken. If it could turn its cameras around, which it cannot, because they were shut off decades ago to conserve power, Earth would be invisible, undetectable, lost in the glare of a star that itself is just a dot. This creates psychological challenges for any future explorers. Human beings evolved on a planet with a dominant light source overhead. Our circadian rhythms, our sense of direction, our emotional well-being are all tied to the presence of a bright star in the sky. What happens to a crew when that anchor shrinks to insignificance? When home becomes literally invisible? Nobody knows. We have never had to find out. The astronauts who traveled to the moon could still see Earth as a disk, blue and white and beautiful. They could point to it in the sky. They knew where home was. At the edge of the solar system, home disappears. You would have to trust your instruments, trust your navigation, trust that the tiny dot you cannot distinguish from 1,000 other tiny dots is really where you came from. The isolation is not just physical, it is perceptual, emotional, absolute. And yet, even from there, you would still be inside the gravitational reach of our star, still technically part of the solar system. The true emptiness lies beyond. Beyond Neptune lies a graveyard of worlds that never were. It is called the Kuiper Belt, and it stretches from roughly 30 to 50 times the distance between Earth and our star. Within this band orbit millions of frozen objects, remnants of the solar system's violent birth, and the evidence of that violence is written across their surfaces. When the solar system formed 4.5 billion years ago, the region beyond Neptune was supposed to produce another planet. The raw material was there. Dust and ice swirled in the outer disk, gradually clumping together under gravity's pull. Given enough time, these clumps should have merged into a world comparable to Uranus or Neptune. It never happened. Something disrupted the process. Most scientists believe Neptune is the culprit. As the giant planets migrated through the early solar system, Neptune swept through the outer region like a wrecking ball. Its gravity scattered the building blocks that should have formed the next planet. Instead of one large world, the region was left with countless fragments. These fragments are still there. Pluto is the most famous, but it is not alone. Eris, Makemake, Haumea, and hundreds of other known objects share the region. Thousands more await discovery. Each one is a piece of the planet that never formed, and they bear the scars of their history. The surfaces of Kuiper Belt objects are cratered, fractured, and battered. Collisions have been constant over billions of years. Objects smash into each other, break apart, and sometimes recombine into new configurations. Haumea, for example, spins so fast that it has been stretched into an elongated shape, probably the result of an ancient impact that also created its 2 moons. These collisions continue today. Every so often, Kuiper Belt objects strike each other with enough force to send fragments flying. Some of those fragments eventually make their way into the inner solar system as comets. The short-period comets that appear regularly in our skies, including famous ones like Halley, originated in the Kuiper Belt. This means the violence of the outer solar system occasionally reaches our doorstep. Understanding the Kuiper Belt helps us understand our own origins. The objects there are frozen time capsules, preserved in the deep cold since the solar system's earliest days. Their compositions tell us what conditions were like in the outer disk. Their orbits tell us how the planets migrated. Their surfaces tell us how much bombardment has occurred over billions of years. The New Horizons spacecraft flew through the Kuiper Belt after its encounter with Pluto in 2015. It visited a small object called Arakoth, a snowman-shaped body about 20 miles long. The images revealed a pristine surface, untouched by the kind of violent impacts common elsewhere. Arakoth had somehow survived relatively intact since the dawn of the solar system. Finding such an object raised new questions. If Arakoth avoided major collisions, were the early conditions in the outer disk different than we thought? How did it form so gently when other objects show evidence of such violence? The Kuiper Belt is not finished revealing its secrets. And the deeper we look, the stranger it becomes. Pluto is dying a slow, cold death, not literally dying, but transforming. As it moves along its elongated orbit, carrying it farther from our star with each passing year, the thin atmosphere that briefly enveloped it is freezing solid and falling to the ground like snow. This is one of the most dramatic seasonal changes in the solar system. Pluto orbits our star once every 248 Earth years. Its path is highly elliptical, bringing it as close as about 2.7 billion miles and carrying it as far as 4.6 billion miles from our star. When New Horizons arrived in 2015, Pluto was about 3 billion miles out and had recently passed its closest approach. At that distance, the dwarf planet receives enough faint warmth to sublimate some of its surface ices. Nitrogen, methane, and carbon monoxide turn directly from solid to gas, creating a thin atmosphere that extends hundreds of miles above the surface. This atmosphere is incredibly delicate, about 100,000 times thinner than Earth's air, but it exists. For a while, as Pluto moves outward on its orbit, the already feeble warmth from our star diminishes further. The surface temperature, which hovers around -380 degrees Fahrenheit even at its warmest, drops further. The gases can no longer remain airborne. They condense. The atmosphere literally freezes and falls as frost. Nitrogen snow settles on the surface. Methane ice accumulates in patches. Carbon monoxide crystallizes. Over the decades of Pluto's long winter, the atmosphere thins to almost nothing. The dwarf planet becomes a frozen, airless world. Then, as the orbit carries it closer again, the cycle reverses. The ices sublimate, the atmosphere rebuilds, and Pluto briefly breathes again. Scientists have been tracking this process from Earth. Observations show that Pluto's atmosphere has been thinning since about 2015, right after New Horizons flew by. The spacecraft arrived at almost the perfect moment, catching Pluto near its atmospheric maximum before the long decline began. This seasonal cycle has profound implications. The surface of Pluto is constantly being reshaped. As ices sublimate in some regions and condense in others, the landscape changes. The famous heart-shaped glacier on Pluto's surface, named Tombaugh Regio, is made of nitrogen ice. It flows slowly, like glaciers on Earth, driven by the subtle temperature differences across the terrain. When the atmosphere collapses, these flows may slow or stop. When it returns, they resume. Over thousands of years, the surface is sculpted by this rhythmic breathing. For future exploration, this matters. Landing on Pluto during its atmospheric phase is different from landing during its frozen phase. The thin air creates faint but real drag. Navigation calculations would differ. Even the landing site itself might change as ices shift. No human mission to Pluto is planned. The distance alone makes it extraordinarily difficult. But robotic explorers may one day return, and when they do, they will find a world that looks different than what New Horizons photographed. Pluto does not stay the same. It breathes with the slow rhythm of its orbit. And right now, it is holding its breath. At the outermost edge of the solar system, our star begins to lose its grip. For billions of miles, our star's gravity is the dominant force. It holds planets in orbit. It shapes the trajectories of comets. It defines the boundaries of everything we consider our cosmic neighborhood. But that dominance has limits. In the outer Oort cloud, roughly 1 light-year from our star, something shifts. The gravitational pull from our star becomes comparable to the cumulative gravitational influence of the entire Milky Way galaxy. This is where the solar system starts to blur into interstellar space. The galaxy is massive beyond comprehension. It contains roughly 200 billion stars, along with vast quantities of gas, dust, and dark matter. All of that mass creates a gravitational field that permeates everything. Here on Earth, that field is far too weak to notice because our star's gravity overwhelms it completely. But at the edge of the Oort cloud, the balance changes. Objects there feel two competing pulls. One comes from our star, weakened by enormous distance but still present. The other comes from the galaxy, a subtle tug created by the combined mass of everything between here and the galactic center. This galactic tide affects orbits in strange ways. Over millions of years, the tidal force can slowly change the shape and orientation of orbits in the outer Oort cloud. It can lift objects out of the plane of the solar system, scattering them into random inclinations. It can nudge objects that were stable into new paths that eventually carry them sunward. Some researchers believe the galactic tide is one of the main mechanisms that sends long-period comets into the inner solar system. A comet drifting peacefully in the outer Oort cloud might be gently tugged by the galaxy's gravity until its orbit shifts just enough to start falling inward. This process is slow. It takes millions of years, but it never stops. The galaxy is always there, always pulling, always reshaping the outermost edge of our solar system. This has implications for the long-term stability of the outer regions. Objects at the very edge of the Oort cloud are not truly bound to our star. They are in a gravitational gray zone, loosely associated with our solar system, but subject to outside influences. Over billions of years, many of them will be stripped away entirely, stolen by passing stars or gradually pulled free by the galactic tide. Our solar system is leaking, not dramatically, not quickly, but over cosmic timescales, material drifts away. The Oort cloud was probably larger in the past. It will probably be smaller in the future. Our star cannot hold everything forever. This is a reminder that the solar system is not isolated. It exists within a larger structure, influenced by forces that operate on scales far beyond our everyday experience. The galaxy shaped us. It continues to shape us. And one day, billions of years from now, it will absorb us entirely when our star dies and its remnants disperse. For now, the edge holds, but only barely. If you could listen to interstellar space, you would hear a hiss. It is faint. It is constant. It comes from every direction equally, and it has been traveling toward you for almost 14 billion years. This is the cosmic microwave background, the afterglow of the Big Bang itself, and Voyager is bathed in it right now. When the universe began, everything was compressed into an unimaginably hot, dense state. As space expanded, it cooled. About 380,000 years after the initial explosion, the universe cooled enough for atoms to form. Before that moment, light could not travel freely because it kept bouncing off free electrons. After that moment, the universe became transparent and light was released. That light has been traveling ever since. Over billions of years, the expansion of the universe has stretched those original light waves. What started as blindingly hot radiation has cooled, to just a few degrees above absolute zero. The wavelength has stretched from visible light into the microwave part of the spectrum, but it still fills all of space. Everywhere in the universe, in every direction, this ancient radiation bathes everything. On Earth, we detect it with specialized instruments. In interstellar space, it is the dominant source of photons. There is nothing else out there producing light in significant quantities. Voyager's instruments were not designed to study the cosmic microwave background. That was never part of the mission, but the spacecraft is surrounded by it nonetheless. Every square inch of its surface is being struck by photons that left their source nearly 14 billion years ago. This radiation carries information. The tiny variations in the cosmic microwave background, slightly warmer in some directions and slightly cooler in others, reveal the structure of the early universe. They show where matter was slightly denser, where galaxies would eventually form, where the seeds of everything we see today were planted. From Earth, we have mapped this radiation in exquisite detail. Satellites like COBE, WMAP, and Planck have created images of the cosmic microwave background that look like static on a television. That static is the oldest light in existence. Voyager cannot create such images. Its instruments lack the sensitivity, and the mission was never designed for cosmology. But symbolically, the spacecraft has traveled far enough that the local noise of the solar system has faded. The cosmic background has become, in some sense, more prominent. This is what the universe sounds like when you get far enough from home. Not silence, a hiss, the echo of creation itself, still ringing after almost 14 billion years, filling every corner of space, reminding everything that exists where it all came from. The Voyagers carry golden records meant to tell any future finders about humanity, but they are also carrying something else, evidence, proof that the universe had a beginning, proof that we figured out what that beginning sounded like. The hiss will never stop. Long after Voyager falls silent, long after our star dies, long after the Milky Way collides with other galaxies, the cosmic microwave background will continue to fade, stretched thinner and thinner by the expansion of space. But for now, it whispers. And if you know how to listen, it tells the oldest story there is. Attached to each Voyager spacecraft is a message in a bottle. It is a golden phonograph record, 12 inches in diameter, plated with gold to resist erosion over cosmic timescales. Encoded on its grooves are sounds and images from Earth. Greetings in 55 languages. Music from around the world. The sound of wind, rain, and laughter. Photographs of humans, animals, and landscapes. This record was designed to outlast human civilization. The committee that created it, led by Carl Sagan, faced an impossible task. How do you communicate with an intelligence that might be utterly alien? How do you explain who you are to something that may not share any of your assumptions about physics, biology, or meaning? They did their best. The record's cover includes diagrams showing how to play it. A stylus is included. Instructions use the hyperfine transition of hydrogen, a universal constant, as a reference for timing and frequency. If any being ever finds this record and figures out how to decode it, they will hear Chuck Berry playing Johnny B. Good. They will see a photograph of a mother nursing her child. They will hear the word hello in languages that may no longer exist. But the odds of anyone ever finding these records are essentially zero. Space is incomprehensibly vast. The Voyagers are heading toward no particular star. Voyager 1 will pass within 1.6 light-years of a star called Gliese 445 in about 40,000 years. But it will not come close enough for the star's gravity to capture it. It will simply drift past. After that, both spacecraft will continue wandering the galaxy for billions of years. They will orbit the center of the Milky Way, occasionally passing through spiral arms, occasionally coming within a few light-years of other stars. The chances of them ever encountering another object, let alone an intelligent civilization capable of finding and interpreting them, are vanishingly small. This was known when the records were made. They were never really intended as practical communication. They were intended as symbols, statements, evidence that humans once existed and dared to send their voices into the void. The records will outlast almost everything else we have built. Long after every building on Earth has crumbled, long after every book has decayed, long after the continents themselves have rearranged beyond recognition, the voyagers will still be drifting, silent, cold, and alone, but still carrying those golden discs. In 5 billion years, our star will exhaust its fuel and expand into a red giant. It will swallow Mercury, Venus, and probably Earth. The inner solar system will be destroyed, but the voyagers will be too far away to be affected. They will drift on, carrying proof that we were here. This is the longest-lasting artifact humanity has ever created, not a monument, not a message carved in stone. 2 small spacecraft, each about the size of a compact car, tumbling slowly through interstellar space with golden records bolted to their sides. If you ever want to feel both the grandeur and the loneliness of human existence, think about those records. Think about the songs playing for no one, the photographs unseen, the greetings unheard, drifting forever. One day, humans may try to leave, not just send robots, not just extend our reach with radio signals, actually leave, board a spacecraft, and travel to the edge of the solar system and beyond. When that day comes, we will face challenges that make every previous exploration look simple. The first problem is time. Voyager 1 has been traveling for nearly 50 years and has only recently entered interstellar space. It is moving at roughly 38,000 miles per hour, which sounds fast until you realize that at this speed, reaching the nearest star would take over 70,000 years. No human could survive such a journey. No human civilization has ever lasted that long. Any crew that departed on such a mission would die long before arrival. Their descendants, if the ship could sustain generations, would be unrecognizable to the people who launched them. Speed is the only solution. To reach another star within a human lifetime, you would need to travel at a significant fraction of the speed of light. Current technology cannot come close to this. Our fastest spacecraft achieve roughly 0.006% of light speed. We would need to improve by a factor of thousands or tens of thousands. Concepts exist: nuclear pulse propulsion, antimatter engines, laser-driven sails. None have been built. None have been tested at scale. The engineering challenges are immense, and the energy requirements are almost unimaginable. The second problem is radiation. As we discussed earlier, cosmic ray levels triple once you leave the heliosphere. Any crewed vessel would need massive shielding or some form of active protection. Passive shielding adds mass, which requires more fuel, which adds more mass. The numbers spiral quickly into impossibility with current materials. Active shielding, using magnetic fields to deflect charged particles, is theoretically possible, but has never been demonstrated at the scale needed, and some cosmic rays are so energetic that no realistic magnetic field could stop them. The third problem is isolation. At the edge of the solar system, communication delays stretch to hours. In interstellar space, they would stretch to years. A crew traveling toward another star would eventually lose real-time contact with Earth entirely. They would be alone in a way no human being has ever experienced. Psychological studies suggest this level of isolation could be devastating. Humans are social creatures. We need connection. A generation ship traveling for centuries might develop entirely new cultures, new languages, new ways of being that bear no resemblance to the civilization that launched them. And yet, we went to the moon with technology that now seems primitive. We sent robots to Mars, to the outer planets, to the edge of the solar system itself. Every barrier that seemed impossible eventually fell to human ingenuity and determination. The edge is far. The challenges are real, but they are not fundamentally different from challenges we have overcome before. They are larger in scale, yes, They require technologies we have not invented yet, yes, but physics does not forbid interstellar travel. It simply makes it hard. Somewhere in the future, perhaps centuries from now, perhaps longer, a human being may look back at our star from interstellar space. They may see it as Voyager sees it now, a bright dot in an ocean of darkness, and they will know that we made it. The edge is not a wall, it is a door. Our solar system has a tail. You cannot see it. No telescope on Earth can photograph it directly, but it exists, stretching behind us as we move through the galaxy, a ghostly wake of charged particles and magnetic fields extending for billions of miles into the darkness we have already passed through. It is called the heliotail, and its discovery changed how we picture our place in the cosmos. For decades, scientists imagined the heliosphere as a roughly spherical bubble. Our star sat at the center, blowing solar wind in all directions, and that wind pushed outward evenly to create a round protective shell. It was a tidy, symmetric picture. The reality is far stranger. As our solar system plows through the interstellar medium at roughly 450,000 miles per hour, the heliosphere gets compressed at the front and stretched at the back. The same way a comet develops a tail when it approaches our star, our entire solar system develops a tail as it moves through galactic space. NASA's Interstellar Boundary Explorer, the same spacecraft that detected the mysterious ribbon, mapped this structure for the first time. The data revealed a heliotail composed of fast and slow-moving particles, twisted by magnetic fields into a shape that scientists compared to a four-leaf clover. The tail extends in the opposite direction from our motion through the galaxy. If you could look at our solar system from outside, from the perspective of an observer watching us pass by, you would see something resembling a cosmic jellyfish, a blunt nose pushing forward, tentacles of charged particles streaming behind. This tail is not stable. It writhes and shifts depending on the activity level of our star. When solar wind is strong, the tail extends farther and becomes more defined. When solar wind weakens, the tail shrinks and becomes more diffuse. The 11-year solar cycle causes the tail to pulse rhythmically, like breathing. But here is what makes the heliotail unsettling. The particles in that tail are essentially lost. They have been stripped from the protective bubble and left behind as we move forward. Over billions of years, our star has been shedding material into the galaxy, leaving a trail of its own substance scattered across interstellar space. We are not just passing through the galaxy, we are dissolving into it. The rate is slow, imperceptibly slow by human standards. But over the 4.5 billion year history of the solar system, a significant amount of solar material has been deposited into the interstellar medium. Atoms that were once part of our star's corona are now drifting between the stars, mixed with material from countless other stellar systems. This means the galaxy is not made of isolated islands. It is a soup. Everything is mixing. Particles from our star mingle with particles from stars that died before our solar system formed. The boundaries between systems are porous. For anyone trying to trace the history of our cosmic neighborhood, the heliotail is evidence. It marks where we have been. In principle, if you could track individual atoms, you could follow our trail back through the galaxy and reconstruct the path our solar system has taken over billions of years. No technology exists to do this. The particles disperse too quickly. But the concept remains profound. We are leaving footprints in the galaxy, and something is following that trail right now. In October 2017, astronomers spotted something that should not have been there. It was moving too fast. Its trajectory was wrong. It was not orbiting our star. It was passing through, falling inward from interstellar space, swinging around our star and heading back out toward the void it came from. They named it Oumuamua, a Hawaiian word meaning scout or messenger. It was the first confirmed visitor from another star system, and it was deeply strange. Oumuamua was small, probably a few hundred feet long, but its shape was unlike any asteroid or comet we had ever seen. Based on how its brightness changed as it tumbled, scientists estimated it was either extremely elongated, like a cigar, or extremely flat, like a pancake. Neither shape is common in our solar system. Even stranger was its behavior. As Oumuamua swung past our star and headed back toward interstellar space, it accelerated slightly, not much, a tiny push that altered its trajectory by a measurable amount. Comets do this when they release gas, but Oumuamua showed no visible coma, no tail, no outgassing that telescopes could detect. Something was pushing it, and nobody could see what. The most likely explanation is that Oumuamua was releasing gas in a way that was simply too faint for our instruments to detect. Perhaps it was made of frozen hydrogen or nitrogen, substances that would sublimate invisibly. Perhaps its surface was unusual in ways we do not understand. Some scientists proposed more exotic ideas. Avi Loeb, a Harvard astronomer, suggested Oumuamua might be an artificial object, a piece of alien technology, perhaps a light sail from a distant civilization. This idea generated enormous controversy. Most astronomers rejected it, pointing out that natural explanations had not been exhausted. But the debate itself revealed something important. We have no way of knowing what interstellar objects should look like. Oumuamua was our first sample size of one. Maybe elongated shapes are common among objects ejected from other star systems. Maybe the mysterious acceleration has a mundane explanation we simply have not thought of yet. What we know for certain is that interstellar objects pass through our solar system regularly. Calculations suggest that at any given moment, there might be thousands of interstellar objects larger than Oumuamua inside Neptune's orbit. Most are too small and dark to detect. They drift in from the void, swing around our star, and depart without anyone noticing. We caught Oumuamua by luck. A new survey telescope happened to spot it just as it was leaving. We had only a few weeks to study it before it faded beyond detection forever. Since then, astronomers have found another interstellar visitor. Comet Borisov, detected in 2019, was clearly a comet with a visible tail. It came from interstellar space, passed through, and departed. Unlike Oumuamua, it looked relatively normal, but the floodgates are open now. New telescopes coming online will detect more interstellar objects. Each one is a message from another star system, a piece of material ejected billions of years ago that wandered the galaxy until chance brought it here. Some of them might be carrying something: organic molecules, complex chemistry, perhaps even dormant microbes, frozen and preserved across interstellar distances. We do not know what is drifting through our solar system at this very moment, but something always is. In interstellar space, Voyager heard something humming. It was not a sound in the traditional sense. Space is a vacuum, and sound waves cannot travel without a medium, but plasma waves can. And when Voyager 1 crossed into interstellar space, its plasma wave instrument began picking up a persistent, low-frequency vibration. Scientists call it the interstellar hum. The plasma in interstellar space, thin as it is, can oscillate. When disturbed, it vibrates at specific frequencies, determined by its density. Voyager's instruments convert these oscillations into audio range frequencies so humans can hear them. The result is an eerie, persistent drone. This hum was unexpected. Inside the heliosphere, the plasma environment is noisy and variable. Solar eruptions create shock waves that ripple outward, causing spikes and fluctuations in plasma wave activity. Scientists expected interstellar space to be quieter, calmer, more uniform. Instead, they found a continuous oscillation. The hum appears to be generated by the constant interaction between the interstellar plasma and low-level disturbances propagating through it. Even in the relative quiet of interstellar space, small perturbations keep the plasma vibrating. It never falls completely silent. But here is where it gets stranger. Occasionally, the hum is interrupted by bursts of activity, shock waves, from our star, coronal mass ejections that propagate outward through the heliosphere, eventually reach interstellar space and disturb the plasma there. When they arrive, the plasma rings like a bell being struck. The frequency shifts, the amplitude spikes. Then, gradually, it settles back to the persistent hum. Voyager has recorded several of these events. Each one takes months to develop and months to fade. The shock waves travel so slowly at that distance that by the time Voyager detects their effects, the solar event that caused them happened years earlier. This creates a strange echo effect. Scientists on Earth can watch a solar eruption happen in real time. They can track the shockwave as it propagates through the inner solar system, passing Mercury, Earth, Mars, the outer planets. And then they wait. Years later, Voyager detects the ripple as it finally reaches interstellar space. The plasma hum tells us something important about the environment beyond the heliosphere. Interstellar space is not static. It has texture. It responds to disturbances. It carries information about events happening both inside and outside our solar system. The hum is a kind of background noise created by all these interactions layered on top of each other. We do not fully understand what creates the baseline oscillation. Some scientists suggest it might be caused by the interaction between the heliosphere and the interstellar medium, a constant low-level turbulence generated where the two environments meet. Others propose it might be related to distant events in the galaxy, shock waves from supernovae, or stellar winds from faraway stars that have propagated across light years to reach our location. The data is still coming in. Voyager continues to record, and the hum continues to drone. It is the sound of interstellar space breathing. Forget the neat diagrams in textbooks. The heliosphere is not a round bubble. It is not symmetric. It is not stable. Recent research suggests it might be shaped like a deflating, lopsided, constantly shifting cosmic creature unlike anything scientists originally imagined. For decades, the standard model showed our star at the center of a comet-shaped bubble. The front would be compressed by the interstellar medium as we plow through it. The back would stretch into a long tail, simple, clean, easy to visualize. Then the data started contradicting the models. Measurements from the Voyagers, from IBEX, from the Cassini spacecraft before it ended its mission, painted a more chaotic picture. The heliosphere appears to be squashed in ways that do not match the simple comet shape. Some models now suggest it looks more like a croissant. Others propose a shape with multiple lobes and bulges, constantly morphing as conditions change. One particularly striking model suggests the heliosphere might not have a long tail at all. Instead of streaming behind us for billions of miles, the solar wind might curl back on itself, creating a compact, almost spherical shape that rides along with us through the galaxy. This would mean the traditional picture is completely wrong. The heliotail might be an illusion created by limited data. The debate is ongoing. What everyone agrees on is that the heliosphere responds dynamically to both internal and external pressures. When our star is active, spewing more material into space, the bubble pushes outward. When our star quiets down, the bubble contracts. When the interstellar medium becomes denser, the bubble compresses. When it becomes thinner, the bubble expands. This means the shape is never fixed. At any given moment, the heliosphere might look different than it did a decade ago or a century ago. The boundary that Voyager crossed in 2012 might have moved significantly since then. The protective cocoon around our solar system is alive, breathing, pulsing with the rhythm of our star and the galaxy around it. For human exploration, this creates problems. You cannot plan a mission to a boundary that will not stay put. The termination shock, the heliopause, the hydrogen wall, all of these features shift over time. A spacecraft designed to study one configuration might arrive to find something completely different. And the shape affects protection. If the heliosphere is more compact than previously thought, the shielded region is smaller. Cosmic rays might penetrate deeper than older models suggested. The safe zone around our star might be a thin skin rather than a thick cushion. We are still learning. Every new measurement from the outer solar system adds to the picture. Every new model tries to reconcile the contradictions. Slowly, a more accurate understanding is emerging. But one thing is clear. Our home is not the stable, predictable bubble we once imagined. It is something stranger, something wilder, and we are only beginning to see its true shape. Space is often described as empty, but that is a dangerous simplification. The interstellar medium contains particles, not many, just a few atoms per cubic inch. But over time, those particles erode everything they touch, and the Voyager spacecraft are being slowly sandblasted by the void. This process is called sputtering. When a fast-moving atom or ion strikes a solid surface, it can knock loose atoms from that surface. In the relative warmth of the inner solar system, surfaces are protected by the solar wind, which sweeps away much of the incoming interstellar material. But once you cross the heliopause, that protection vanishes. Voyager is now traveling through a thin soup of interstellar hydrogen, helium, and trace heavier elements. The spacecraft is moving at roughly 38,000 miles per hour relative to this material. From the perspective of the particles, Voyager is slamming into them at high speed. From the perspective of Voyager, the particles are bombarding its surface continuously. Each impact is tiny. A single atom striking the spacecraft does essentially nothing. But there are many atoms, and there is a lot of time. Over millions of years, this bombardment will degrade Voyager's structure. The golden record will erode. The metal surfaces will pit and scar. Thin components will be worn through. Given enough time, the entire spacecraft will be reduced to a cloud of drifting atoms dispersed into the interstellar medium it once traveled through. This process will take an almost unimaginable amount of time. Estimates suggest the Voyagers could remain recognizable for hundreds of millions of years, possibly longer. But they will not last forever. Nothing does. The interstellar medium is patient. This erosion also affects any natural object traveling through interstellar space. The Oort cloud comets have been exposed to this environment for billions of years. Their surfaces have been processed by cosmic rays, sputtered by interstellar particles, and altered by the slow accumulation of damage. When a comet falls inward toward our star, the fresh ice below the surface sublimates and creates the familiar tail. But the crust, the outer layer that faced the void, carries a record of its time in interstellar space. It is darker, more processed, more radiation damaged than the pristine interior. For future spacecraft, this erosion sets limits on mission duration. Any probe we send into interstellar space will eventually fail. Electronics will degrade, surfaces will erode, seals will breach. The environment is not actively hostile in the way a planet with acid rain might be, but it is relentless. It wears things down. Even the most robust spacecraft we could build would eventually succumb. This is a humbling thought. We can send our machines into the void, but we cannot make them last forever. The galaxy will slowly disassemble everything we create, atom by atom, over timescales that dwarf human comprehension. The Voyagers are fighting this battle right now. Every second, particles strike their surfaces. Every second, atoms are knocked loose. They are dissolving, so slowly that it barely matters, but dissolving nonetheless. This is a thought experiment, but the science behind it is real. Imagine a human body exposed to the conditions at the edge of the solar system. No spacecraft, no suit, just flesh and bone in the void beyond the heliosphere. What would happen? First, the obvious. You would die, instantly, more or less. The vacuum would pull the air from your lungs. The moisture in your eyes and mouth would boil away as the pressure dropped. Your blood would not boil immediately because your skin would hold the pressure in, but unconsciousness would come within 15 seconds, death within a minute or two. But then something strange would happen. Nothing. Your body would not rot. Decomposition requires bacteria, and bacteria require warmth, moisture, and oxygen. In the vacuum of deep space, At temperatures approaching absolute zero, no biological process can continue. The microorganisms that would normally break down tissue would freeze solid along with everything else. Your body would freeze dry. The remaining moisture would sublimate slowly over time, turning directly from ice to vapor and drifting away. What remained would be a desiccated husk, frozen harder than any ice on Earth, preserved in the cold and dark. This mummy would remain largely intact for an almost incomprehensible span of time. Without oxygen, there would be no oxidation. Without moisture, there would be no chemical reactions requiring water. Without warmth, molecular motion would slow to nearly nothing. The only forces acting on the body would be the slow sputtering from interstellar particles and the constant bombardment of cosmic rays. Cosmic rays would eventually alter the chemistry of the tissues. Over millions of years, they would break molecular bonds, creating damage similar to extreme radiation exposure. But the body would not disappear. It would simply become more and more degraded at the molecular level while retaining its overall shape. Sputtering would erode the surface extremely slowly. The outermost layer of skin would gradually be worn away, atom by atom. Over hundreds of millions of years, this erosion might become significant. But the timescales are so vast that the body would remain recognizable far longer than any human structure on Earth. If left undisturbed, your frozen corpse could drift through the galaxy for billions of years. It would outlast every building, every monument, every fossil record on Earth. It would outlast the continents, the oceans, perhaps even our star itself. Long after our home planet has been swallowed by a dying red giant, your remains could still be tumbling through interstellar space. This is not a comforting thought, but it reveals something important about the environment at the edge of the solar system. The void preserves the same conditions that make it deadly to living things, make it a nearly perfect storage medium for anything that can survive the initial transition. Voyager's golden record will last for hundreds of millions of years because there is nothing out there to destroy it quickly. In a universe where entropy claims everything eventually, the cold, dark spaces between stars are the closest thing to permanence that exists. Your body would become a monument, drifting forever through a silence no one would ever break. Everything we have discussed so far represents what we know: the termination shock, the heliopause, the Oort cloud, the cosmic radiation, the magnetic mysteries, the interstellar hum. All of these are features we discovered because we thought to look for them, because our theories predicted something, because our instruments were designed to measure something. But history teaches us that the greatest discoveries are often the ones nobody anticipated. When Voyager launched in 1977, scientists expected it to find certain things at Jupiter and Saturn. They expected moons with craters. They expected magnetic fields with certain properties. They expected radiation belts. What they found instead reshaped planetary science. Active volcanoes on Io, something no one had predicted. A subsurface ocean on Europa, now considered one of the most promising places to search for extraterrestrial life. Geysers on Enceladus, hydrocarbon lakes on Titan, the rings of Saturn far more complex than any model had suggested. Each destination held surprises that changed our understanding of what was possible. The edge of the solar system has already begun to deliver its own surprises. The ibex ribbon, the magnetic field discrepancies, the unexpected structure of the heliosheath. Every time we extend our reach, we find something that forces us to revise our assumptions. What else is waiting out there? We do not know. That is the point. Perhaps there are structures in the Oort cloud that defy current understanding. Perhaps the transition to interstellar space involves physics we have not yet described. Perhaps the interstellar medium contains phenomena we lack the instruments to detect. Perhaps the galaxy itself is stranger than our models allow. This is why exploration matters. Not because we know what we will find, but precisely because we do not. Every probe we send, every measurement we take, every photon we capture from the outer darkness adds to our understanding of a universe that is far more complex than any human could have imagined a few centuries ago. The edge of the solar system is not an ending. It is a doorway to questions we have not yet thought to ask. Voyager is still transmitting. New Horizons is still traveling outward. Future missions are being planned. Each one carries instruments designed to answer current questions, but each one will inevitably discover something unexpected. That is the pattern of science. That is the rhythm of discovery. We predict, we observe, we are surprised, we revise, and then we reach farther. The edge is calling. It always has been. Since humans first looked up at the night sky and wondered what lay beyond the visible stars, we have been drawn toward the unknown. Now we are finally beginning to touch it. The Voyagers have crossed the boundary. They have entered interstellar space. They have sent back data that no human has ever seen before, but they are just the beginning. The true exploration of the edge, the deep understanding of what lies beyond our protective bubble, is work for future generations. Work for spacecraft we have not yet built. Work for scientists who have not yet been born. They will find things that terrify them. They will find things that inspire them. They will find things that change everything. The edge is not empty. It is waiting. And we are finally learning how to listen.